Hello students, in today's lecture we are going to discuss the Poynting theorem. So this Poynting theorem is a very important concept and mathematical derivation which is included in the syllabus of BTech students under AKGEC University. So as far as the background of this Poynting theorem is considered, basically all of us know that whenever our electromagnetic waves move in a medium, they always transport energy along their motion. And we know that electromagnetic radiation is made up of both electric and magnetic field vectors, which are mutually perpendicular to each other. And they are also perpendicular to the direction of the propagation because electromagnetic radiation is of transverse nature. So whenever electromagnetic waves move in any medium, they will always transport our energy. So this concept of Poynting theorem is basically related to this energy transportation itself. So in this electromagnetic field theory, energy in an electromagnetic field, Poynting vector and Poynting theorem, and significance of different terms in the Poynting theorem. So these are the target of today's lecture. So first of all, let us understand the concept of Poynting theorem. The rate of energy transfers per unit volume from a region of space equals to the rate of work done on a charge distribution plus the energy flux leaving at the region. A second statement can also explain the theorem. The decrease in the electromagnetic energy per unit time in a certain volume is equal to the sum of the work done by the field forces and the net outward flux per unit time. So the Poynting theorem, in this Poynting theorem, the term Poynting vector is also included, and the Poynting vector P is represented by the cross product of E vector and H vector. So P is equal to E cross H. So basically this Poynting vector P is equal to E cross H, and the magnitude of this Poynting vector basically tells us about the energy which is flowing in outward direction from any closed surface which is bounding any volume, of course, and that surface area is perpendicular to the direction of propagation. So this Poynting vector will represent that term. So for driving this mathematical relation, we have to use the Maxwell's equation, particularly the Maxwell's third equation and Maxwell's fourth equation. So the general term for the Maxwell's fourth equation is del cross H is equal to J plus curly D over curly T, or del cross H is equal to J plus DD over DT. This is Maxwell's fourth equation. That is curl of H, magnetic intensity field vector, that is equal to J, that is the current density, plus rate of change of electric displacement vector. This is our Maxwell's fourth equation. So in this derivation, we will use both Maxwell equation, third as well as fourth. Now from this Maxwell's fourth equation, we can easily estimate the value of J. So the value of J comes out to be J is equal to del cross H minus DD over DT. Or we can write J is equal to del cross H minus epsilon dE by dt. So here we have changed D is equal to epsilon into E for any medium. D is a electric displacement vector, and that is equal to epsilon, that is the permittivity of medium, multiplied by the electric field vector E. So D is equal to epsilon E. Since E is a constant quantity, so we can take that E outside this derivation. So J will be equal to del cross H minus epsilon dE over dt. So this is our Maxwell's fourth equation. Now let us take the dot product of this equation from both sides. Let's take the dot product of this equation from both sides. So when we'll take a dot product, so what we will get? We will get E dot J is equal to E dot del cross H minus E dot dd over dt, and that is equal to E dot del cross H minus epsilon E dot E multiplied epsilon E dot dE by dt. So we all of us know that D is equal to epsilon E, and we have taken the epsilon outside. So this will become epsilon into E product of dE by dt. So this is now, we have named this equation as equation number 1. So we have arrived at this conclusion by using the Maxwell's fourth equation and taking the dot product of that fourth equation from both sides with the electric field vector E. Now, from the vector identity theorem, we know that divergence of E cross H is equal to H dot del cross E minus E dot del cross H. So this comes out from the vector identity theorem, which is generally derived in the vector calculus. So we are using the concept of vector calculus. So from this theorem, we can write E dot, this term E dot del cross H is equal to H dot del cross E minus del E cross H, divergence of del dot E cross H. This is our equation number 2. So now we can use this value of E dot del cross H here from this equation number 2 in equation number 1. So after substituting this value of E dot del cross H, that is equal to H dot del cross E minus divergence del dot E cross H in equation number 1, what we will get? We will get this kind of relation, that is E dot J is equal to H dot del cross E minus del dot E cross H minus epsilon E into dE by dt. So this whole term we have substituted from the equation number 2, So this was our equation number 2. Now, E dot del cross H is equal to H dot del cross E minus del dot E cross H. So we have substituted this value from equation number 2 here in equation number 1 in place of E dot del cross H. Okay. Now, the value of E dot J is equal to H dot minus dB by dt. So this value of del cross E we have substituted equal to minus dB over dt. So from where this value has come? This value has come from Maxwell's equation 3. So according to Maxwell's third equation, all of us know that curl of E, what is Maxwell's third equation? This is del cross E is equal to minus of dB over dt. So this is our Maxwell's third equation. Del cross E is equal to minus dB over dt. So we have substituted here the value of del cross E from this relation. This is Maxwell's third equation. This is Maxwell's third equation. So use this equation and substitute the value of curl of E. So curl of E or del cross E is equal to minus dB over dt. So in this way, we can say that value of E dot J is equal to H dot minus dB over dt minus del dot E cross H minus epsilon E dot dE over dt. Now all of us know that value of B is equal to mu into H. B is equal to mu into H. So here we will replace this B by mu into H. So this equation can now be written as H dot minus mu dH by dt minus del dot E cross H minus epsilon E dot dE by dt. Or this can be also written as minus mu, we can take this minus mu outside, that is minus mu H dot dH over dt minus epsilon naught E dot dE over dt minus divergence of E cross H, del dot E cross H. So this is the final form. This equation is now known as equation number 3. So basically in this equation number 3, what we are getting that E dot J is equal to mu H dot dH by dt minus epsilon E dot dE by dt minus divergence E cross H, that is del dot E cross H. Now by very simple mathematics, we can prove that value of H dot dH by dt is exactly equal to half d over dt into H square. This can be very easily seen by doing the back calculation. D over dt half mu H square. So this will be equal to, we can take we can take half outside. So when we will differentiate, so T2 will be here, mu can be also taken B, and H dot dH upon dt. So 2 will get cancelled, and what we will get? Simply we will get mu H dot dH over dt. This is the value of d over dt. D over dt of half mu h square. Half mu h square. This is equal to this mu h dot dH by dt. So in this way, mu h dot dH by dt is equal to half of d by dt into h square. We can also take this mu inside the differentiation because it is a constant quantity. It is not going to make any difference there in the differentiation. Similarly, we can write for E dot dE by dt is equal to half of d over dt into E square. Now substituting all these values in equation number 4, from equation number 4, in equation number 3, what we will get? We will get this term, that is E dot j is equal to minus mu half d over dt h square minus epsilon half d over dt E square minus divergence of E cross H. So as I've told you earlier, because since mu and epsilon, they are the constant quantity, the permeability of a free space and the permittivity of a medium and the permeability of medium, sorry. So we can take both these terms inside here in the differentiation. So we can write minus d over dt mu h square by t minus d over dt epsilon E square by 2 minus divergence of E cross H. Now these two terms can be little bit rearranged and they can be written as minus d over dt mu h square by t plus epsilon E square by t minus divergence of E cross H, and this is now written as equation number 5. So what we are getting in equation number 5? In equation number 5, we are getting E dot j is equal to minus d over dt mu h square by t plus epsilon E square by 2 minus divergence of E cross H. Now by integrating this whole equation number 5 from both sides, okay, with respect to V. Now by integrating this equation from both sides with respect to volume, what we will get? We will get integration of E dot j dV is equal to minus d over dt integration mu h square by 2 plus epsilon E square by 2 dV minus integration divergence of E cross H with volume integration. So this is the mathematical statement we are getting for the Poynting theorem. So basically in this term, what we were getting integration of volume integration of E dot j dV is equal to minus d over dt integration, volume integration mu h square by 2 plus epsilon E square by 2 dV minus volume integration divergence of E cross H dV. Now in this last term, we can apply here Gauss divergence theorem. So after applying the Gauss divergence theorem, so we can easily convert this volume integration into surface integration. So that means this term integration divergence of E cross H into dV, this will be simply equal to, this is the volume integration, this will be changed into the surface integration. This will be simply E cross H into ds. So we have used here Gauss divergence theorem. So basically this Gauss divergence theorem is utilized in vector calculus for converting the volume integration into surface integration, and it's vice versa. So here we are converting this volume integration into surface integration. And in this way, our equation has been changed in this way. So volume integration E dot j dV is equal to minus d over dt volume integration mu h square by 2 plus epsilon E square by 2 into dV minus surface integration E cross H into ds. So in this last term, we have changed the volume integration into surface integration. So now we have to understand the physical significance of all these three terms separately. So for that purpose, let us little bit mathematically rearrange this equation and let us take this E cross H ds on the left side. So what we will get, E cross H ds surface integration with respect to S, that is equal to volume integration E dot J dV plus d over dt volume integration mu h square by 2 plus epsilon E square by 2 dV. So first of all, let us understand the physical significance of this term E cross H ds. So as I have told you students that this E cross H represents the Poynting vector, which is simply representing the energy which is flowing in outward direction perpendicular to the surface area S, which is bounding some volume V. And when we will take its integration form, so that will represent its total amount. So it is representing the total amount of energy which is leaving any surface area which is perpendicular to the direction of propagation. So this term is also known as the ingoing power flux over the surface. The power flux which is either entering any closed surface or it is leaving the closed surface. So that is equal to volume integration of E dot J dV plus d over dt volume integration of mu h square by 2 plus epsilon E square by 2. Now, this final term mu h square by 2, this represents the magnetostatic energy, and the term epsilon E square by 2, this represents the electrostatic energy. And combinedly, these two terms are known as the electromagnetic energy stored in the volume. So once again, I am repeating the first term mu h square by 2, this represents the magnetic energy stored within the volume, and the second term epsilon E square by 2, this represents the electrostatic energy stored in the volume. So their entire summation is going to tell us about the total electromagnetic energy stored in the volume. So when, let's say that when some according to the Poynting theorem, the energy which is ingoing inside any closed surface S, so that will be equal to the total dissipated power within the volume V. So this first term will represent the loss of power. Very mathematically, very easily we can show that this terms E dot J, this represents equal to electrical power dissipated in the volume V. And this final terms, this represents the rate of decrease of the total electromagnetic energy stored within the volume V. So when we can say that in a nutshell, when this radiation is leaving any closed surface, then that will be equal to the total dissipated power within the volume plus rate of decrease of total electromagnetic energy inside that volume. Now for this term is quite obvious that mu h square represents the magnetic energy, epsilon E square, this terms represent the electric energy, and their net sum is known as the electromagnetic energy. So as far as this term E dot J is concerned, so we can easily show that this is equal to the total dissipated power within the volume V. E is electric field vector and J is the current density. So this can be written as E dot, for J surface current density, J is equal to I divided by the area. Now E can be written as V upon D. So I upon A. Now this A and D will combinedly represent a volume and V into I will represent the power. So power per unit volume. The total dissipated power per unit volume, and in integral term this will represent the total power dissipated within the volume V. So this is the mathematical significance of the different terms which are introduced in this derivation of Poynting theorem. So Let's once again review its different mathematical derivation related terms once again for the better clarity. So the rate of energy transfer per unit volume from a region of a space equals to the rate of work done on a charge distribution plus the energy flux leaving that region. So if energy flux will leave any region, so that will be equal to the work done on a charge distribution and energy transfer per unit volume. So for driving it, let's once again quickly have a review. So we started the derivation with Maxwell's fourth equation, that was del cross H is equal to J plus dd over dt. So from this equation, we find out the value of J. J is equal to del cross H minus dd over dt, or J is equal to del cross H minus epsilon dE by dt, because this D is a electric displacement vector which is equal to epsilon into E. Now on taking the dot product of this equation from both sides, what we will get? We will get E dot J is equal to E dot del cross H minus E dot dd over dt, and the value of D is epsilon E. So we can write this E dot del cross H minus epsilon E dot dE by dt. Now by using the identity from vector calculus, we know that divergence of E cross H is equal to H dot del cross E minus E dot del cross H. So here we have to find this value of E dot del cross H. So value of E dot del cross H is equal to H dot del cross E minus del dot E cross H from equation number 2. So from equation number 2, we have to substitute the value of E dot del cross H here in the equation number 1. So we get this term now. E dot J is equal to H dot del cross E minus del dot E cross H minus epsilon E into dE by dt. So as I explained you earlier, that value of del cross E according to Maxwell's third equation is equal to minus dB over dt, and B is equal to mu H. So this will be H dot minus mu dH over dt minus divergence of E cross H minus epsilon E dot dE by dt. So after rearranging, what we will get? We will get E dot J is equal to minus mu H dot dH over dt minus epsilon E dot dE over dt minus divergence of E cross H, and this has been written in the form of equation number 3. Now H dot dH over dt is equal to half of d by dH square. Similarly, E dot dE by dt is equal to half of d over dt epsilon E square, as I explained you earlier. So by substituting these values from equation number 4 in equation number 3, what we will get? We will get this form. E dot J is equal to minus mu half d over dt H square minus epsilon half d over dt into E square minus del dot E cross H. So this can be written as E dot J is equal to minus d over dt mu. We can take this mu inside the differentiation. So this will be E dot J is equal to minus d over dt mu H square by 2 minus d over dt epsilon E square by 2 minus divergence of E cross H. So this value of E dot J is equal to minus d over dt. We have combined these two terms and taken the differentiation outside the bracket. So E dot J is equal to minus d over dt mu H square by 2 plus epsilon E square by 2 minus divergence of E cross H. This is our equation number 5. Now integrating this equation number 5 with respect to volume from both sides, we will get volume integration E dot J dV is equal to minus d over dt volume integration mu H square by 2 plus epsilon E square by 2 dV minus volume integration divergence of E cross H dV. Now this final term, divergence of E cross H, we have to change this term from volume integration into surface integration by using the Gauss divergence theorem. So finally, this equation can be written in this form, that is volume integration E dot J dV, that is equal to minus d over dt volume integration mu H square by 2 plus epsilon E square by 2 dV minus surface integration E cross H ds. And in this way, this completes the mathematical derivation of Poynting theorem. So quickly, let's once again explain the physical significance of various terms which have been included in this derivation. So the first term, E cross H, that represents the ingoing power flux over the surface area S, which is represented by Poynting vector, and E dot J, this represents the total dissipated power within a volume V, or the loss of power, and mu h square by 2 and epsilon e square by 2, they represents the magnetic energy and electrostatic energy respectively. And their summation is known as the electromagnetic energy. So this term will represent the change or the decrement in the electromagnetic energy within the volume V. So this is the significance of different mathematical terms in this Poynting theorem derivations. So this was all about in this lecture about Poynting theorem. Thank you to all of you.